Hello everyone. Topic is reactivity order of 1 degree, 2 degree, 3 degree haloalkanes toward beta elimination reaction. In previous video we have understood beta elimination reaction and its mechanism. And one more point that I want to clear to the students, beta elimination reaction mechanisms like E1 and E2 are not in the CBSE board syllabus. So you can directly perform the reactions, and if you want to understand the mechanisms, they are available there. Next, let's understand reactivity order of 1 degree, 2 degree, 3 degree haloalkanes toward beta elimination reaction. First, we need to understand what are 1 degree haloalkanes. Check this haloalkane. The carbon is connected to the halogen, which is further directly connected with one carbon. So this is 1 degree haloalkane. If we have such condition, this will be 2 degree haloalkane. The carbon to which halogen is connected is further directly connected to two carbons, so 2 degree haloalkanes. Similarly, we can have this carbon which is connected with halogen and further connected with 3 carbons, so it is 3 degree haloalkane. Now, these three type of haloalkanes, if are undergoing to beta elimination reaction, for example, let's draw them. Br I am using over here. This is 2 degree, and here I am drawing 3 degree. Now suppose it is reacting with KOH alcoholic strong base. It is also reacting with KOH alcoholic strong base. It is also reacting with KOH alcoholic strong base. Means the conditions are perfect for beta elimination. Okay. In previous video I told you how to make a direct product. The trick was beta hydrogen and halogen. Just remove it and make double bond over here. So when 1 degree, this is 1 degree haloalkane, this is 2 degree, and this is 3 degree. When 1 degree haloalkane will show beta elimination reaction, I will get this alkene. When 2 degree will show, actually here we have two type of beta hydrogens. This is beta carbon, this is beta carbon, but they will give same kind of alkene because they are similar. So suppose I am using this hydrogen and Br I am eliminating from alpha position. So when this hydrogen I will use for elimination, bond between these two carbons will generate and it will become this. Same here, this is alpha carbon. We have two beta carbons. This is beta carbon, this is beta carbon, this is beta carbon. Any beta carbon you can use, all will give you a same alkene. Suppose I am using this hydrogen and this Br I am going to eliminate. So bond between these two carbons will generate. So the next product will be CH3, C double bond, CH2 and CH3 as it is. This alkene will generate. Now 3 degree, 1 degree, 2 degree. Which haloalkane will be fastest in these reactions? Now this we can understand in two ways. First way is just count beta hydrogens. Like on this, how many beta hydrogens are there in 1 degree? 1, 2, 3. 3 beta hydrogens are there. 3 beta hydrogens. In 2 degree, how many beta hydrogens are there? 1, 2, 3, 4, 5, 6. 6 beta hydrogens are there. And in 3 degree, we have 9 beta hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 beta hydrogens. So obviously more beta hydrogens, more fast reaction it will be. Means 3 degree haloalkanes will be fastest in beta elimination reactions because they are carrying more beta hydrogens. Next way is just check the stability of alkenes which are formed. Let me tell you, this alkene is least stable and the alkene which is generated from 3 degree will be most stable. How to check stability of alkene? Let's understand. Suppose this is alkene, the next carbon, this is doubly bonded carbon, the next carbon is known as alpha carbon. Just count alpha hydrogens. Suppose if I am talking about this alkene, how many alpha hydrogens are there? 6 alpha hydrogens are there. These 6 alpha hydrogens will show hyperconjugation. Hyperconjugation effect. In 11th class, we have understood about hyperconjugation. Hyperconjugation is providing stabilities to the alkene. And amount of hyperconjugation is decided by number of alpha hydrogens. More alpha hydrogens, more hyperconjugation, more stability. So to every time compare the stability of alkene, count alpha hydrogens. More alpha hydrogen, alkene will be more stable. Less alpha hydrogen, alkene will be less stable, because alpha hydrogens are deciding amount of hyperconjugation. So in 1 degree, the alkene I got this one. 1 degree haloalkane provided me alkene, this one. From 1 degree haloalkane, I got this alkene. 2 degree haloalkane provided me this alkane, this alkene. And 3 degree haloalkane provided me this alkene. Now let's compare the stability of alkene. What I said, alkenes will be compared, alkene stabilities will be compared by counting alpha hydrogens. So, do we have alpha hydrogen in this alkene? No alpha hydrogen. Alpha carbons are not available, so no alpha hydrogen. No alpha hydrogen, no hyperconjugation. Let's check this one. These are the 2 carbons, doubly bonded carbons. Which carbon is alpha carbon? This one. How many hydrogens are there? 1, 2, 3. So it is carrying 3 alpha hydrogens. Means here we have hyperconjugation. And here we don't have hyperconjugation. Means this alkene is better than this. Now let's check third one. This is doubly bonded carbon. Around this carbon we don't have any alpha carbon, but around this carbon we have 2 alpha carbons, this and this. How many alpha hydrogens are there? 6 alpha hydrogens are there. Means this alkene is most stable alkene out of these 3. That's it. This is the topic. 1 degree haloalkane is giving us this alkene which don't have any alpha hydrogen. 2 degree haloalkane is giving us the alkene which is stabilized by 3 alpha hydrogens through hyperconjugation. And 3 degree haloalkane is providing us this alkene which is stabilized by 6 alpha hydrogen through hyperconjugation. So because 3 degree haloalkane is able to create stabilized alkene, that's why 3 degree haloalkane will show fastest beta elimination reaction. And 1 degree haloalkane is giving us unstable alkene, so that's why 1 degree haloalkane is least reactive toward beta elimination reaction. So what will be the final order? If I write reactivity order of 1 degree, 2 degree and 3 degree haloalkanes toward beta elimination reaction, so increasing order will be this. 1 degree will be least reactive, 2 degree haloalkanes will be more reactive than 1 degree, and 3 degree haloalkanes will be most reactive toward beta elimination reaction. Reasons are, in 2 ways you can understand. Either count beta hydrogens. In 3 degree haloalkane, we have highest number of beta hydrogens. So obviously it will be most reactive toward beta elimination reaction. Second reason, it is providing us most stable alkene. So that's why 3 degree haloalkanes are ready for beta elimination reaction, because product is most stable. Now, one more point. If we have a haloalkane which is able to produce 2 type of alkenes. Like suppose this is the haloalkane and we are making it to undergo for beta elimination reaction by reacting it with strong base like CH3, CCH3, CH3, O negative, Na positive. Strong base, sodium tert butoxide I am using. Okay, so the condition is available for beta elimination reaction. Yes, beta hydrogens are there and strong base is there. Now we have two type of beta carbons. This is alpha, to which halogen is connected. This is alpha, this is beta, and this is beta. If we are using this beta hydrogen and eliminating chlorine, so I will get this alkene, check. This hydrogen and this chlorine will be eliminated out and double bond will generate here between these two carbon. So the alkene will be this. And if I am using this beta hydrogen and I am eliminating this chlorine, so then I will get this alkene. Check. This will remain as it is, CH3, CH. Now double bond will come between these two carbons. Here, this one. And CH3 as it is. Now out of these two alkenes, first of all check, are they same? No, they are not same. Means two type of alkenes are possible by this haloalkane. Now which will be major alkene? Note down. More stable alkene will be major product and less stable alkene will be minor product. How we will check stabilities? Right now we have done through alpha hydrogens. This is doubly bonded carbon, these are doubly bonded carbon. What is alpha carbon? This is alpha carbon. How many alpha hydrogens are there? Two are there. Two alpha hydrogens will show hyperconjugation. Two alpha hydrogen. Let's check how many alpha hydrogens are this side. This is doubly bonded carbon, these are doubly bonded carbon. This is alpha carbon carrying how many alpha hydrogens? 3 alpha hydrogen. This is also alpha carbon carrying how many alpha hydrogens? 3. So total 6 alpha hydrogens are there. This alkene is stabilized by 6 alpha hydrogen through hyperconjugation, and this alkene is getting stability through 2 alpha hydrogen by hyperconjugation. Means this alkene is more stable and this is less stable. That's why this will be the major product and this will be the minor product. So please keep this point in your mind also. When two alkenes are possible, the major alkene will be a stable alkene and minor alkene will be a less stable alkene. And how to check stability of alkene? By counting alpha hydrogens. More alpha hydrogen, more stability of alkene. Now, this rule, what is the rule now? The haloalkanes which can produce two type of alkene, major alkene will be more stable and minor alkene will be less stable. This we call Sagev rule. Sagev rule. When two type of alkenes are possible by a haloalkane through beta elimination reaction, the more stable alkene will be a major product and less stable alkene will be a minor product. So that's it. This is the end of the topic. Thank you very much.